Hello, everyone. My name is Natalia Korsakova. I'm a postdoc at APC, and I will talk today about the LISA data analysis, and I'm very thankful of being able to talk about that on behalf of all the people who work on this topic. I will organize my talk in such a way that I will try to go through different sources that we are going to observe in LISA, and then I will give a sort of baseline data analysis that we are at the moment, and describe the challenges that we are facing and the steps that have been done to overcome these challenges. First, for those who don't look at the LISA data on the daily basis, I want to show how the data looks in the time domain. Nora already have shown how it looks in the frequency domain and how you can see all the different signals that come into that. But here, so we can see, for example, the galactic binaries. If we look at the couple of them that we usually call verification galactic binaries, that they would be quite easy. They would be almost monochromatic signals. If we put on top of them one MRI, the signal are already starting to look much more complicated. And then if we put on top just a single massive black hole, we can see that this higher CNS signal basically dominates our time domain output. If we put on top of these signals also all the galactic binaries from our galaxy, we see them as a sort of kind of noise on top of this signal. And then if we also add noise, then we stop seeing anything. This shows us that a first step in our data analysis is an important which data representation we choose, if we choose time domain, frequency domain, or time frequency domain, and that can be different for different source types. And this also how they look in the frequency domain. So in my presentation, the overall scheme, how we do data analysis, can be presented in a sort of following way. So first thing is that we have to do pre-processing, because the data that we are going to observe from the interferometers will be contaminated by the high level of the laser frequency noise. And to get rid of this frequency noise, we have to do pre-processing. And for this pre-processing, we will have a dedicated plenary talk on Tuesday from Olaf Hartvig. Then, when we have our TDI combinations with which we are usually used to work in terms of data analysis, we do an iterative process of parameter estimation for different source types. And this iterative process we usually call global fit. And about global fit, you will have a dedicated plenary talk by Michael Katz on Thursday in the morning. And also, in addition to that, on Friday afternoon, there will be a dedicated session with parallel talks with different group contributions to resolving this problem. And as the output of our data analysis that we then deliver to the astronomers, we will have catalogs or alerts for the fast estimation of the massive black hole binaries. So I want to start with going through different type of signals. I will start with a stochastic background. So stochastic background will be a superposition of the many weak incoherent sources, and we will have two types of background. One is the signals that come from the astrophysical origin, such as, for example, the background from the galactic binaries, and the other is the background that is coming from the cosmological origin. Most studies thus far assume that the background is stationary, isotropic, and Gaussian. And it is actually a very complicated problem to separate the background of the cosmological or astrophysical origin from the noise. Because in the ground-based detectors, for example, they rely on the fact that can do the cross-correlation between different independent detectors. And in LISA, we are not going to have independent detectors. Therefore, it is becoming a very hard problem. And there have been many methods developed in recent years, and we can roughly separate them into different classes. So it's where people assume certain template for their background, or they assume certain template for their noise. And both of this assumption relies on the fact that we either have to know something about the signal in advance, or we have to know something about the noise in advance. So to know something about the signal in advance, we can get this knowledge, for example, from populations. We can get knowledge on their astrophysical background. From some models from fundamental physics, we can know assumptions on their background of their for the cosmological background, and from what Martin has presented, maybe we would know some knowledge on the noise in advance. So the most straightforward way to think of this problem is when we have a template on the noise and template on the signal, and then we try to understand the parameters of our signal. There have been some studies when they assume that they don't know anything about the noise, and then they try to find the known signal in this unknown noise. And also there have been studies when they assume that they know the noise but don't know the signal, and they are moving forward in the direction of having no assumption neither on the noise or on the signal. So let me go through some basic concepts for all of these approaches. So when we have the template for the noise and for the signal, this is a kind of most straightforward approach. In this case, we assume that the model of the stochastic background is some sort of power law, and then for this power law, we try to reconstruct the amplitude and the spectral index. And for the noise, we can assume some noise from the science requirements, for example. There have been a recent work when they extended this approach by trying to see if the knowledge on the anisotropic nature of the astrophysical background from the galactic binary can help separate the astrophysical background from the cosmological background. And they have found that if they would have two detectors present, that would be a great benefit, but that would be not such a big help in the case if we have one detector. For the cases when we have the template on the noise, but we don't know anything about the signal, one of the approaches to do this is when we separate our spectral band into the bins. And then in each of the bins, we fit the power law, but that allows us to fit very complicated shapes and very non-trivial profiles. And this method is very widely used in the community. And the other method, it simply tries to look in the excess of power. And by looking at this excess of power, they try to see the signal over the noise. In both of these approaches, they don't really fix the noise, but they allow some sort of variation on that, and they estimate the level of this variation, but they fix the noise profile. In the very recent work, they try to use Gaussian processes for estimating both the parameters of the signal and parameters of the noise. And the step forward in that work is that they also allow for they start with a theoretical model of the noise, but they allow also for the variation of the shape of the noise. And the last kind of subset of this approach is how to tackle the work with a cosmological background, cosmological and astrophysical backgrounds is when they assume the template for the signal and then they try to fit the noise. So they fit the noise actually directly to the interferometer levels, and also they, instead of working with AET orthogonal combinations, they work with X, Y, Z, and so they don't assume this orthogonality of AET by default, which is very important because there also have been another work recently from Olaf Hartig, who studied whether these AET combinations, they are actually orthogonal. And he has shown that in the case when we have non-equal arms, they are not really orthogonal. And in addition to that, even if we have the secondary noises in the interferometers, if they're going to be different, this also breaks the assumption of the orthogonality. And in this plot, you can see that the usual T combination that was quite widely assumed that this would be the combination when we would only see the noise and no signals. In the case if we have non-equal arm lengths, it gets almost the same sensitivity as the A and E. And he comes up with another combination that might be actually better for studying the backgrounds. Now we are going to switch from the backgrounds and go to the galactic binaries. We will see the background, astrophysical background from the galactic binaries, but at the same time, we are going to see a lot of resolvable galactic binaries. If we have one single galactic binary, it is very easy to analyze it because it's practically, well, one single galactic binary would look like that. It is a very narrow band, almost monochromatic signal, and we have very fast waveforms with response for them. But in reality, we are going to have many of them. Therefore, we will have a problem that we will have a lot of overlapping signals that will have correlated parameters. And in addition to that, we wouldn't know even how many signals we are going to have in each band. And this is a big problem that is being addressed in the global fit. And you can see the talk on this from Michael Katz. This would be one of the problems that he would discuss, and also again this plenary, parallel session on Friday. We separate some of the galactic binaries, which we call verification binaries, because these are the signals that we have already seen in the electromagnetic spectrum, and they're sort of signals that we expect that we're going to see. And if you are interested in this, there is a catalog of the signals that are being maintained, and there will be a talk from Tyson where he will specifically talk about the data analysis for the sources and how the knowledge on their astrophysical properties from electromagnetic observations can help data analysis. When we find all our parameters for galactic binaries, the question is that how we are going to produce the final data products, or how we call them, the catalogs that we are going to deliver to the community of the astronomers. This is also a big, not entirely resolved problem, and there have been some studies already for results of the single global fit, but we still have to understand how we do this if we have several global fits together and how we unite them with each other. And also we have to think of what goes into our data. So what populations of the galactic binaries goes into our observation. At the moment, we were analyzing data that was produced based on one of the population models, but there are several of them, and if we take into account this population model that would go into our data, we can also do a hierarchical parameter estimation for these models as a result of the global fit. Next, binary signals now are massive black hole binaries, and for them, I want to draw your attention to their morphology of the signals, because they can be very different. So for very massive black hole binaries, you will have almost transient signals, but for low mass massive black hole binaries, you would have long-lasting signals that can last for months, and this would need different analysis approaches to analyze that type of signals. To analyze them thus far, we inherit the knowledge on the waveforms from the ground-based detectors. Thus far, we have been using mostly phenome family of the waveforms, and one of the kind of research that is going on now is to try to move from these simple waveforms and try to include eccentricities and precession. And it is also very important to develop acceleration techniques for massive black hole binaries. So one of the recent papers have studied the structure of the physical parameter space of the massive black hole binaries, and there is the paper from Sylvain Marsat, and he discusses that you can theoretically show that there will be a degeneracy in the sky position, and there will be 3 modes in these sky position degeneracies. And by knowing these 8 modes, you can help yourself while, for example, performing your parameter estimation, because when you find one of the modes, you would know where you can position all our other 7 modes. And it is, again, to mention that it is important to move to more elaborate waveforms. Here we can see the posterior distributions for one of the massive black hole binaries, and in blue you see the posteriors that were done with a simple phenom D waveform. But if you include higher harmonics, you get much better estimation of the parameters, and your posteriors look much nicer. You get much better sky localization. So it again shows us that we have to use better waveforms. Thus far, we have been working with response in the frequency domain for these waveforms, but for ring down, for example, people typically use the time domain. Also, again, the importance of more precise waveforms. There will be 2 talks that will show that which systematics we can get in the parameter estimation by mismodeling the waveforms, especially at such high SNRs. And also there have been some studies and some people try to perform parameter estimation, including the waveforms that have a precession in them. And so I want to mention that it is for parameter estimation of massive black hole binaries, the acceleration techniques are very important, and one of the methods that is not new but is very widely used is the so-called heterodyning technique. And this method relies on the fact that we separate our parameter estimation in two parts, that we first search for the signal, and then we kind of expand our waveforms around the waveform that we found by searching. And these methods, they have been also extended recently to the processing waveforms. Last but not the least, it is very important for the alerts and for the multi-messenger astronomy to get the early warnings. And this plot shows you how based on like how much time is it till the merger, how good will you know the localization of the massive black hole based on the gravitational wave signal, and then you can provide this knowledge on the localization to the electromagnetic astronomers. And for this type of analysis, for producing early warnings for electromagnetic observations, it is important to do the parameter estimation fast. So there have been quite a lot of work, and there will be a couple of posters during the poster session dedicated on the different way to do the parameter estimation. So instead of using the sampling techniques such as MC or nested sampling, we can use another techniques such as for example, normalizing flows. Now let's switch to stellar massive black hole binaries. So for stellar massive black hole binaries, there have been many works that explored the parameter estimation. In the case, if we kind of assume that we know where to start the parameter estimation from. But the search problem is quite hard. And the search problem is a kind of first step to address the search problem for MRIs, which is extremely hard. And that brings us to, to the our last source, extreme acceleration spirals, which is the most difficult source in terms of data analysis. Because their signal modeling is hard, they have very complicated waveforms that are rich in their harmonic content, very complicated parameter space, and the kind of volume of the parameter space is much larger than for their equal mass massive black holes. This is just to understand how complicated these waveforms are. So this is a galactic binary, massive black hole binary. This is just a dominant harmonic of an MRI, and this is if we plot all the harmonics. And MRI search have been addressed quite long ago during the last data challenges that were dedicated to MRIs. And they came up with a semi-coherent search and some stochastic methods. But you can see here that they were like, this is the correct solution, and they were walking towards the correct solution. But at the time, the evaluation of the waveforms took a lot of time, and it was really hard. So now, hopefully, we're in a much better state. We have a GPU-accelerated waveforms that are not completely correct, so they are still describe only Schwarzschild space-time, and their frequency evolution is accurate up to the leading adiabatic order. But this is a very big step, and you can see that how much use of the GPUs are going to speed up these waveforms. And in addition to that, we have accelerated methods to do a response in the time domain, because this is very important to have a response, and for these signals we don't have a fast response in the Fourier domain. However, these waveforms, they are not yet full waveforms. So they don't take into account the second order cell force. And here you can see, and you can also see the talk by Ole Berke on Tuesday, how important is it to include the second order cell force, because otherwise you're going to get biases in the parameter estimation. And you can see also a plenary talk from Adam Pound where he will describe the cell force approach. So waveforms are hard. They're hard, and they're hard to make them fast, but also the parameter space is very complicated. So there have been 2 works recently from Alvin Chure, where he described how degenerate the parameter space is, and so how hard it is to search through this parameter space. On this plot, you can see the green dots. They're the secondary modes. So you end up here, and you have all the secondary modes, and you don't know how to select through the secondary modes. And then the red square is somewhere where the true signal lies. And then you can zoom in, and then you zoom in, and so basically it is extremely complicated problem. And another difficulty that lies in possible incorrectness of the waveforms is that if you, for example, there has been a study that's shown if you don't account for environmental effects that can affect your waveform and your parameter estimation, you can misinterpret these environmental effects by saying that you detect deviations from the general relativity. And I want to finish the description of the MRIs by saying that in addition to that, we have very uncertain populations on them. So we say that at the moment that we can see maybe from 1 to several thousands of them. So if we have several thousands, that means that we will also have the astrophysical backgrounds from MRIs. And sorry, I'm out of time, but I'm going to finish in just 2 minutes, just to mention that in addition to all these nice signals, we're going to have non-nice noise artifacts, and we have to take them into account. And there have been quite a lot of work done recently, and there will be a poster by Jacob Slutsky where I think he can summarize all of this work. So main work was done on the glitches, and we have a data set that we're trying to analyze, and there will be 2 talks on Friday dedicated to that. And also there have been a lot of work on the gaps where people either try to fill the gaps or they look how these gaps would affect the detectability and parameter estimation, and look how people can, for example, work with wavelet data representation to account for the gaps. To analyze the data, we create the different data sets that help us to benchmark our analysis, and I will leave you with a summary, and thank you very much for your attention.
Thank you, Natalia, and I'm sorry about mixing up the agenda in there. No problem. Okay, we have 2 minutes left. Questions? Is there anything left that you wanted to know? There, the microphone, please. Follow my arm.
Hi, yeah, thanks. I actually have a question about parameter estimation for MRIs. And their detectability. In the case of, you mentioned, right, that there might be deviations from GR that we have to worry about due to gas torques on the objects, but in those cases, we might also expect a preferred set of parameters, right? The gas will also tend to circularize the incoming object and put it at 0 inclination angle. And so does that help matters at all? Are those more detectable? Is there, from a signals processing perspective, is that good news, bad news, or doesn't actually matter?
So this work is from Lorenzo Sperry, who has been already mentioned before. It is you can ask him this particular question, but as far as understood, it's actually you can have an effect from the you can have a bias that comes from the environmental effect that you can misinterpret as the deviations from GR. So it's not that these effects, they cause this, but that you can misinterpret them if you don't model them properly. So if you don't properly include them in the waveforms.
Oh, okay, all right, I'll hit Lorenzo up later.
Yeah.
One last. You have about -5 seconds.
Sorry, I just wanted to make a quick comment on that. So yes, if you can find sort of systems in which you have these environmental or modified GR effects which tend to circularize the orbit, that could help you to make that a smoking gun for the presence of these systems. But at the same time, all of these models are phenomenological and based on something that we have taken from planetary migration around in like protoplanetary disks and stuff. So these are very simplistic models, and as soon as you add a little bit of eccentricity in the system, these models tend to break. And I think there's some work being done in including eccentricity in it and see how this inclusion helps in evolving the model, but it seems like even after adding eccentricity, the circularization of the orbits may or may not happen. So in the context of EMRI specifically, even with disks, you can have high eccentricity or low eccentricity orbits. So, yeah. Thanks.
Thank you very much. We are at 10:32.